Similarly, as Nicholas Copernicus presented the heliocentric model, one more dazzling correction of how we might interpret the universe could arise, igniting a discussion known as the emergency of cosmology. This emergency is marked by huge disparities in our estimations and comprehension of the universe's key properties, such as its age, size, and pace of expansion. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has intensified this discussion with a picture that defies physics. So, what exactly is this emergency, and how does the James Webb Space Telescope contribute to it? Well, contribute is a bit of a distortion. More like a review has been underway. The emergency refers to a point where our understanding of the universe is challenged, particularly regarding its age and size, which are tied together by an impressive safety buffer. The introduction of the JWST has been vital in this context. Before this cutting-edge telescope, we were limited in how far we could see into the early universe. Yet with the JWST's advanced capabilities, astronomers can now explore much more distant galaxies, providing us with new perspectives on the universe and challenging some of our previous conceptions. This advancement allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming. These observations offer critical data that can either support or challenge our current models of the universe. To understand the emergency in detail, it is essential to first review the standard model of cosmology, known as the hot inflationary Big Bang model or the lambda cold dark matter, lambda CDM model. This model has been highly successful in explaining various features of the universe, from gravitational lensing to the structure of the cosmic web and the evolution of galaxies. The lambda CDM model posits that the universe began with a massive explosion followed by a period of rapid expansion and has been expanding ever since. It includes components such as dark matter, which exerts gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, every groundbreaking observation, especially with instruments as advanced as the JWST, raises the possibility that our current model may be incomplete or needs revision. The lambda CDM model makes specific predictions about the characteristics and behavior of galaxies at different stages of the universe's history. For instance, it predicts that galaxies in the distant past should be smaller, less developed, and contain fewer heavy elements compared to those we observe in the local universe. This is because heavier elements are formed in the cores of stars and distributed through processes like supernova explosions, which take time to occur. According to this model, galaxies should appear smaller, bluer, and less evolved at greater cosmic distances. This prediction suggests that at some point in the past, the universe would lack visible stars or galaxies. However, scientists have found evidence that challenges these predictions, resulting in what is now called a crisis in cosmology. This crisis centers on the uncertainty about the age of the universe. Different measurement techniques yield different results, leading cosmologists to struggle to reconcile these discrepancies. To address this issue, scientists use several methods to measure the age of the universe. One approach involves studying cosmic background radiation, which involves decoding the history of the universe's expansion and using mathematical models, such as the Friedmann equations based on Einstein's theory of general relativity, to determine the expansion rate and thus the universe's age at different points in time. The cosmic microwave background, CMB, a remnant radiation from the early universe, is a crucial tool for this measurement. Detailed maps of the CMB, such as those provided by the European Space Agency's Planck mission, offer valuable insights into the universe's composition. However, these maps lack information on dark energy, a significant component of the current universe. Despite this limitation, scientists can use the Friedmann equations, along with other observations, to estimate the expansion rate of the universe over time and ultimately determine its age. Another method for determining the universe's age involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles because they have a known intrinsic brightness. By comparing their known brightness to their observed brightness, astronomers can calculate their distance and, consequently, the expansion rate of the universe at different times. This method, used during the 1990s, played a pivotal role in the discovery of dark energy, which is now fundamental to cosmological measurements. It is particularly useful for determining the Hubble constant, a measure of the universe's expansion rate. Although the Hubble constant is not precisely constant, it is instrumental in charting the universe's expansion since the Big Bang roughly 13.8 billion years ago. Observations show that the universe has been growing steadily. NASA has noted the implications of this rate. If the expansion is slowing, it suggests the influence of an unknown force, potentially dark matter. On the other hand, if the expansion rate is accelerating, it could indicate the presence and influence of dark energy driving the universe's growth. In January 2018, researchers observed an intriguing phenomenon. While some telescopes measured variations in the expansion rate of the universe depending on the point of observation, the Gaia Space Telescope recorded a faster expansion rate in the nearby universe, while the Planck telescope measured a slightly slower expansion in more distant regions. This discrepancy highlights the vast size of the universe and reminds us of the pioneering work of Edwin Hubble, who first proposed the universe's expansion rate in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, demonstrating that the universe is expanding, a cornerstone of modern cosmology. Hubble's groundbreaking work established a foundation for understanding the expanding universe. However, with modern advancements like the James Webb Space Telescope, JWST, the precision of our observations has reached new heights, revealing discrepancies that challenge the standard lambda-CDM model. These discrepancies manifest most notably in the varying measurements of the Hubble constant, which indicate differences in the universe's expansion rate depending on the method or region observed. The JWST's ability to peer deeper into space and time has uncovered galaxies that appear more developed than expected based on the lambda-CDM model. For instance, galaxies from the early universe, only a few 100 million years after the Big Bang, have been observed to contain heavier elements and more complex structures than predicted. These findings question the timelines of galaxy formation and the processes through which heavier elements were synthesized. Additionally, the JWST has provided more detailed images of galaxy clusters, revealing gravitational lensing effects that challenge our understanding of dark matter's distribution. These observations suggest that the theoretical models of dark matter and its interactions may require significant refinement. The crisis in cosmology, thus, revolves around reconciling these new observations with existing theories. Some scientists propose that the discrepancies might indicate unknown physics beyond the standard model, such as variations in the fundamental constants of nature or new interactions involving dark energy and dark matter. Others suggest that the crisis could stem from systematic errors in measurements or assumptions embedded in the lambda-CDM model. As research continues, astronomers are leveraging the JWST and other observatories to refine their models and gather more data. These efforts are critical, not just for resolving the crisis but for deepening our understanding of the universe's origin, evolution, and ultimate fate. In the coming years, cosmologists hope to achieve a unified model that accounts for the early universe's unexpected complexity, the apparent tensions in the Hubble constant, and the role of dark matter and dark energy. Until then, the emergency of cosmology serves as both a challenge and an opportunity, one that could lead to transformative insights about the cosmos. Cosmology is presently considering the development of the universe. Freely observing an enormous area, you would witness similar phenomena at the same speed, corresponding to the Hubble expansion rate. Initial computations relied on limited data, but with technological advances, such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our measurements. Various telescopes use readings of the cosmic microwave background, CMB, to calculate the constant, although this method has its limitations due to the availability of supernovae for distant observations, which restricts our view of the universe. Since the discovery of dark energy in the 20th century, scientists have grappled with the disparities between these two approaches to determining the age of the universe and its expansion rate. As measurement technology becomes more precise, smaller variations emerge, driven by the development of more advanced systems. This progress, unexpectedly, raises further questions rather than providing definitive answers. Although the differences are minimal, just 10 to 20 million years, these discrepancies remain significant, given that the universe is approximately 13.77 billion years old, warranting careful investigation. One possible explanation for this discrepancy is the potential for flaws in our measurements of the CMB. Despite being one of the most accurate measurements, it has been extensively tested since its launch in 2003 to validate its precision. Another perspective suggests a potential gap in our understanding of dark matter, proposing that it might vary over time and be linked to dark energy or some other unknown factor. This possibility has led to numerous experimental studies. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Resolving this uncertainty in supernova models could help address the disparity in measurements. This crisis in cosmology has been further intensified by the discoveries of the James Webb Space Telescope, JWST. According to Neil deGrasse Tyson, the JWST has uncovered objects in the universe that challenge our current understanding. This implies that our scientific framework needs a complete overhaul, but the problem is that we have no clear starting point. To grasp the magnitude of this scientific upheaval, let's examine the origins of the universe. Around 150 million years after the Big Bang, stars, black holes, and star clusters began to emerge, possibly as early as 50 to 100 million years later. However, these events should have been relatively rare. What we don't know is how common galaxies became in later times, spanning events between 200 and 400 million years after the Big Bang. Recent JWST images reveal galaxies much more distant, and therefore older, than the standard cosmological model predicts. This discrepancy suggests that our model needs significant revision. The discovery that the expanding universe relies on galaxies is a fundamental development. JWST images show galaxies that formed much earlier than expected by current cosmological models, triggering a crisis in the field. This issue is related to galaxies and redshift, a common measurement in cosmology. According to the Standard Model, hydrogen began to appear 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This transformed the universe into a soup of hydrogen atoms with some helium and residual background radiation. Gravity then acted on small perturbations in this hydrogen gas, gradually collapsing them to form the first stars. These early stars, primarily composed of helium and hydrogen, underwent nuclear fusion, creating heavier elements such as carbon and nitrogen. These elements played a critical role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages, including the merging of smaller structures to form larger ones and the continuous formation of new stars from interstellar gas. However, the JWST has observed galaxies that formed significantly earlier than predicted by our current models, suggesting that we may need to rethink our understanding of the early universe. This new data challenges existing theories and raises questions about the processes that led to the formation of the first galaxies. The implications of these discoveries are profound, as they could lead to a major shift in our understanding of the universe and its origins. In summary, the crisis in cosmology highlights the challenges and uncertainties we face in understanding the fundamental properties of the universe. The James Webb Space Telescope has provided valuable new data that challenges existing models and prompts us to reconsider our theories. This ongoing process of discovery and revision is a testament to the dynamic nature of scientific inquiry and the ever-evolving understanding of the universe. The crisis in cosmology not only affects our understanding of the universe's age and expansion but also raises questions about the very fabric of reality. Recent discoveries challenge the assumptions underlying many cosmological theories. For example, the presence of galaxies that formed much earlier than previously believed suggests that our timeline for cosmic evolution may need substantial adjustments. Additionally, data from the JWST indicates that the processes driving galaxy formation could be more complex than current models suggest. Specifically, these findings prompt a re-evaluation of how galaxies interact with their environment, including the role of gas inflow and outflow in their growth. This interaction may influence star formation rates, leading to a different understanding of how galaxies evolve over time. Furthermore, the relationship between dark matter and ordinary matter is becoming a focal point for further research. Observations suggest that dark matter may play a crucial role in galaxy formation and behavior, affecting how visible matter is distributed within galaxies. As scientists delve deeper into this relationship, They may uncover new physics that could bridge the gaps in our current understanding. Astrophysical simulations are also advancing alongside observational developments. These simulations can incorporate new findings from telescopes like the JWST, allowing researchers to model galaxy formation and evolution with greater accuracy. By integrating various astrophysical processes, such as supernova feedback and cosmic gas dynamics, simulations can provide insights into the conditions that led to the formation of the first galaxies. The interplay between observational data and theoretical models is essential in refining our understanding of cosmology. As more data becomes available, scientists will have the opportunity to test existing theories against new observations. This iterative process is fundamental to scientific progress, enabling researchers to adapt and refine their models to reflect the complexities of the universe. Ultimately, these discoveries highlight the dynamic and ever-changing nature of cosmological inquiry. Each groundbreaking observation can serve as a catalyst for deeper exploration, leading to revisions that could redefine our understanding of the universe. As we continue to explore the cosmos, the potential for groundbreaking discoveries remains immense, keeping the spirit of inquiry alive in the field of cosmology.